So in a last lecture, we discussed that Maxwell found some problem with this particular equation and Maxwell wanted to modify this equation. So let us see what problem did Maxwell find. So Maxwell gave the following argument. He said that, okay, let me look at this Amperes circuital law, and Amperes circuital law says that if you have a wire and if this wire carries a particular current I, yes, I agree, then this current carrying wire produces a magnetic field which are circular by nature. Great. And Biot-Savart's law gave us the formula which says that magnetic field was actually mu naught I divided by 2 pi r. So everything is okay. So r is the radius in which you are finding the magnetic field. For example, from here to here, this can be r, or if you are calculating somewhere around a bigger circle, then this can be r. So r is the position in which you are calculating your magnetic field. Maxwell gave the following argument. He said that consider this circuit. Okay, Maxwell presented the following argument. He said that consider a circuit in which you have a battery of potential V, okay, and you have two capacitors. I mean, you have a capacitor system, and what happens? He says initially, in the end, so when the capacitance has the same potential as the battery, there is no flow of current. So that is at the end. So Maxwell said, no, I am not concerned what happens in the end. I am concerned what happens in between. So Maxwell said that the moment I connect the battery to the capacitor, there is a current in the circuit. Agreed? Now current flows in the circuit. So it goes here, it goes here, and the current flows here. And yes, the current flows in this part of the circuit, and the current flows here, and the current returns to the negative potential. Agreed? So a current is maintained in this particular circuit. Now he presented the argument. He said that let us apply Amperes law here. So what does Amperes law here says? It says that if I consider this particular wire, let me draw green. So if I consider this particular piece of wire as a straight line and the current passing through it as I, then obviously for the yellow line I will have my circular magnetic field. And for this yellow line I can write the integration B dot dl is equals to mu naught I. Agreed? He said that I can write the Amperes law and in this position, in this part of the circuit. He said that we really face problem when we consider Amperes law in this part of the circuit. He says that in this part of the circuit there is no current passing through this particular circle. So he said that if there is no current passing through this particular circle, then Amperes law says that integration B dot dl, okay, is 0 for this second case. But then Maxwell argues it should not be, because the current is actually here and the current somehow passes this part and the current appears on the other part. It means when the current is passing through the vacuum part, it means the current is going from this part to this part in a different form. In what form, that we need to find out, but it is passing from this part to the other part in a different form. So what is the form in which the current is passing from one part of the capacitor to other part? Intuitively, if you look at a capacitor, what happens in a capacitor? So as the charge increases, as the capacitor starts developing a voltage, there is a plus Q charge developed here, and minus Q charge starts developing on the capacitor. Now as we continue, the current becomes less and less, and more is the charges that are getting accumulated on the capacitor. So when the charge in the capacitor is increasing, then obviously the electric field in between the space, okay, what is the nature of electric field? The electric field goes from positive to negative. So electric field in this space is also increasing. So that's an interesting thing. So Maxwell somehow doubted that the electric field, so this electric field might be something in whose form the current here is traveling to the other side. So this gave us a hint that somehow current, when it reaches this portion of the capacitor, gets converted into this electric field. But what electric field, like a changing electric field or constant electric field, we don't know, but somehow we know that it changes itself into the form of the electric field, and then it appears on the other side as current. Agreed? Now let us continue our discussion. So Maxwell said, what happens in a capacitor actually? We know that the electric field is in a capacitor is given by sigma by epsilon naught a, that can be written as q by epsilon naught a. Okay, sigma q by epsilon naught. We have derived this again and again, but here the charge is a function of time, because as the capacitor is gaining the voltage of the battery, as it is trying to gain or reach the same voltage at the battery, more and more charges are getting accumulated. So if I say that the charge on the capacitor is changing with time, then it is quite logical to say that the electric field this side is also changing with time. So this is the first hint that inside the capacitor system the electric field is changing with time. So this is hint number 1. But we actually need to find current. Remember what is the formula of current? So current is always dq by dt, that is rate of change of charge. So Maxwell thought that, okay, why not consider the change of this charge as the current. I mean, see, this is the charge on the capacitor. Agreed? The q is the charge on the capacitor, and Maxwell said that as the charge on the capacitor is changing, invisibly the current from here is going to the other side. It means I can write the displacement current. By displacement current I mean, see, the current is going invisibly in between the capacitor, and that invisible current I say as the displacement current. So inside the capacitor the current is somehow becoming invisible, and I gave the name of that invisible current as displacement current, and this displacement current must be related to the rate of change of charge on the capacitor with respect to time. So if I do d by dt of q, then what am I left with? So I'm left with E naught A as it is, and I need to differentiate the electric field because electric field is constantly changing. So Maxwell argued that when the current goes from this part to this part, he argued that in between the current is invisibly passing through the empty space of capacitor as changing electric field. Agreed? As the changing electric field. So Maxwell said that, okay, so this is the extra modification that I need to do in this equation. So this was the Maxwell's idea. Okay, we're still not done. So so this is I displacement. So I displacement can be written in a more better way. If I multiply the area with the field, then I get the electric flux. So I can write E naught d electric flux divided by dt. Agreed? Now see, this is in terms of id, so in terms of current. So remember the integral form of Maxwell equation. The integral form said integration b dot dl is equals to, so closed integration is equals to mu naught I. So Maxwell said that wait, not only there will be a mu naught I, he said that there will be a mu naught I displacement, because in the places where there is vacuum, current can also pass, but it can pass as a changing electric field. So he said that okay, take mu naught common, put the current I as it is, and put the value of ID. So what is the value of ID? It is epsilon naught d phi, so d phi by dt. But this is the integral form. So when you convert it into the differential form, what happens is you get del cross B. Okay, so the first term is as it is, that is the mu naught J. So that is mu naught J plus the second term will be mu naught epsilon naught del electric field, because you see when we go to the differential form, nearly the area gets cancelled. So by logic I can say that this is the modified Maxwell equation. So Maxwell made a modification in the Ampere circuital equation. Okay, so he made the modification not only in the integral form of the equation, but then he incorporated his modification in his differential form. So let us write the 4 Maxwell equation correctly. So this part will have some modification. So the modification that was proposed by Maxwell was an extra addition of term mu naught epsilon naught del E by del T. Del E by del T. So Maxwell is happy with this term. Maxwell was happy with this term. Why Maxwell is happy? Because this particular extra addition of term created a symmetry between the second and the third equation. So what is the symmetry? You see, the second equation is saying that a changing electric field can be responsible for a magnetic field, and a changing magnetic field can be responsible for an electric field. This is the symmetry that was brought by Maxwell after modifying the Amperes circuital law. This was a great step, and this led to something unbelievable. The 4 Maxwell equation with the modification that Maxwell did, he was able to prove that there are waves called as the electromagnetic waves, which are the waves that contains the electric field and magnetic field, and these waves, they travel at a speed of light. And he also proved that these waves, they need no material medium for the transfer of the wave. Like every other wave needs a material medium, but this electromagnetic wave, that whose presence he predicted by using the 4 Maxwell equations, he said that these electromagnetic waves need no material medium. So in the next lecture, we'll see the power of Maxwell equations. We'll see the real power of Maxwell equation and how he arrived at the concept of electromagnetic wave. So at that time, the concept of electromagnetic wave was completely unknown, and people even didn't know what is the nature of light. Okay, we'll discuss it in the next lecture.